Beyond the Qubit. My name is Frank Dekker and I'm your host. Today's guest is Koen Groenland, physicist, author of Introduction to Quantum Computing for Business and coordinator of startup hub Quantum Amsterdam. His focus is on quantum software. Koen works at the intersection of academia and entrepreneurship, helping to translate quantum research into real-world applications through Quantum Amsterdam. Before we start with the podcast, I have an important disclosure. This is a personal podcast and I do not represent any organization out there. Welcome, Koen.
Yeah, thank you.
Coming back to the application side, you said, okay, yes, a lot of people cite molecular modeling, either for medicines or for materials. And there we can optimize, but you said we can have more impact on society if we can solve machine learning problems. Really,
Yes,
optimization. Is that the correct summary?
absolutely. Yeah,
And then in your book, what I really liked is you explained there's a difference between logical qubits and logical qubits. Can you
absolutely.
explain what the difference between logical qubits and logical qubits is? And then you mentioned the error fault rate. So how
Yes.
many nines about the dot do we need to have logical qubits? And there are different definitions of logical qubits. Can you elaborate a little bit on that?
Yeah, thank you for bringing this up. I think there's a main misconception that people say, oh, somebody built a logical qubit. And then there's the immediate assumption that logical qubits are perfect, that they don't make any mistakes whatsoever. But logical qubits are equally prone to errors. The only thing is, the point of a logical qubit is to exponentially suppress errors compared to what a regular bare physical qubit does. But still, exponentially suppressing that is still maybe not enough, because the amount of steps, the number of steps that we need to do to run a quantum algorithm is so extremely huge. Imagine if you leave your computer on for just 5 minutes, it's making 1 billion steps per second. So the number of steps that you do, even to run a pretty simple computation, is huge. So also, if a logical qubit makes one mistake in, let's say, 1,000 steps or 10,000 steps or 1,000,000 steps, that's definitely not good enough. So we need to somehow push the number of errors, like the frequency of errors that a logical qubit makes, that needs to be pushed to the inverse of the number of steps that your algorithm needs. So if your algorithm needs roughly 1 billion steps, then the error margin is like 1 in 1 billion. So then it's still likely that there is some kind of a mistake. You might need to do the computation multiple times, but if you're in that ballpark, we are quite confident that we can do useful computations.
And I think in your book, Koen, you have a very excellent picture that describes this. Would you be able to share that with the audience afterwards? Or would you be comfortable if I share maybe a link to your book?
Yeah, absolutely. It's published under an open access license, so you can just take the pictures and show them.
It's perfect, thank you. But then you also explain the depth and the amount of steps. So for machine learning and optimization problems, what is the depth, the width, and the steps that we need? So you said, okay, if we go to bigger amount of logical qubits, then is it the width and the steps? Oh, please help me out here.
Yes, yeah, we use jargon called width to represent the number of qubits that are needed for an algorithm, and the depth to represent the number of steps that you do. So I really imagine sort of a rectangle that has a certain width and a certain depth, and that represents the number of, well, the resources that you need in order to do something. You might also say, if I want to play a modern computer game or so, I also need to have a certain width, a certain amount of RAM on my computer to run it. And the depth is not really there on classical computers because they really don't make any mistakes. So classical computers always have infinite depth in this language. Quantum computers, because they do make mistakes, they are only good for algorithms that are only so and so long, that only take so and so many steps.
Maybe to summarize, the quantum computing has two issues. First of all, it's in-memory compute, so they cannot store the data.
Yes.
And secondly, they make errors.
Yes, absolutely.
And because of that, we need the width and the depth. Is that correct to say?
Yes, yeah. I think that's a simplified picture, but a very useful picture to look at.
Yes. And then if we want to do optimization problem, like machine learning for for logistics or for financials,
How much
what
do
is
we
the
need?
yeah, exactly. What is the minimum that we need?
It's very hard to say because, as we said earlier, most of these algorithms we have not, maybe we have not found the algorithms yet, and for those that we are experimenting with, we cannot prove how well they work. So we really have to find out. We really have to just play
And
around and discover this.
why can we not prove? Is it because the hardware is not yet there, or the software is not yet there, or both, or are there other reasons why we cannot prove it yet?
Yeah, but when I say prove, I really mean like proving on a piece of paper. So really a mathematical proof that something would take a certain number of steps. So when we have the hardware, I guess then we will have very much evidence whether an algorithm works or not and how many resources we actually need. But I can give you maybe an indication of what is needed for stuff where we do understand the width and the depth of an algorithm. So
Yes, please.
for example, to crack encryption, that's an example that I love because it's very clean. You either break the encryption or you don't. There's not something in between. So we know exactly when we have solved the problem. So for modern RSA encryption, what's typically assumed is that you need a few thousand logical qubits, let's say around 4,000 or so. And the number of steps, when I look mainly at the most complicated steps to do, that is a few billion. There's multiple definitions of how you compute, so it could be a bit more, a bit less, but several billion, so 10 to the power 9, 10 to the power 10, that's the order of difficult steps that you need to make. So also the error of your qubits needs to go down to the inverse, so 1 in a billion, compared to, let's say, 1 in 100 that we have today.
And what does this mean for machine learning, quantum machine learning, optimization problems? Because there we also need machine learning is based on estimating parameters and big data. But with the current amount of qubits, quantum is not good at the moment in big data.
Absolutely. Yeah, this is one of the reasons I would not recommend to focus too much on quantum machine learning. At first hand, it sounds fantastic because machine learning works amazingly well. Quantum is a very promising technology. So everybody's first reaction is if you put that together, you have something revolutionary. But there are two reasons why I'm skeptical about it. One of them is what you already mentioned. Quantum is not very good at loading or reading large amounts of data, which is typically assumed to be, which is typically the thing that we do with machine learning today, right? Big data, learning from many experiences. And there's a second reason. We discussed that quantum computers have only an advantage if you have a really, really good algorithm. An algorithm that really is an improvement over what we can do classically. But machine learning is precisely the area where we have very good classical algorithms. So if we're going to search for a niche where quantum computers are really good, we should search for stuff where we don't have good classical algorithms. So if I combine these two, right, we need to look at places where classical algorithms are lacking and where we don't need a lot of data. You might look at what I would call small data problems, or professionals call it optimization.
Yes, exactly.
Is it clear why optimization is different from machine learning? Why, for example, if you want to do...
No, that's not yet clear. Please dive a little bit deeper. So I'm aware of small data, and that people refer, say, okay, optimization. So maybe to summarize, machine learning is really for big data, and optimization you mean more for small data. But then really highly complicated issues that you cannot easily solve. And I call it the depth is much bigger. So on a small amount of data, you try to calculate much more complex things, which a normal computer does not have the amount of computational power to solve. Is that a good summary, Koen?
Yeah, absolutely. Yeah, I think that's well said. I think it's important to realize, for example, if you want to train ChatGPT, you need terabytes, maybe petabytes of data to train it on. But the kind of optimization problem that you can imagine is, for example, if you are a package delivery company and you have, let's say, 50 delivery vehicles and you need to deliver 1,000 packages on a day, which packages do you put on which vehicle and how do you route the vehicles? Which path do they drive? That's a complicated problem. It has an exponential number of possibilities. But to store this amount of data, like 1,000 packages, 50 vehicles, that's not a lot of storage compared to the terabytes that you need in machine learning tasks. Or also if you want to schedule a roster of personnel, of staff, that all, you always need to have a certain number of staff available, but they also need their breaks. They also need their holiday hours. Who has to work at which moment? That's another example of a difficult optimization problem.
And can you explain for the audience who's not so familiar with quantum, what can a quantum computer solve that the normal computer cannot do in the small data area?
If I'm totally honest, then the answer is we don't know. There's no proof that a quantum computer is much faster. I know that there are several papers, several claims where people have shown that quantum computers are in some regard better than what they compared with classically. But I'm not convinced by that. What I want to see is a well-studied problem that people care about, that people in the field of classical computing have worked on. Maybe people in machine learning or people in operations research. They have tried to solve the problem the best they can. And then a quantum computer comes by and solves the same problem somehow in a better way. For example, because they achieve a more accurate result or because they do it faster. So I want to see proper benchmarks. And so far, we've not seen any really relevant benchmarks where a quantum computer was faster. And looking at the scale of quantum computers today, I don't expect it in the next couple of years.
And why is it? Is it because the hardware is not good enough, or that the software is not good enough, or there are no quantum algorithms good enough?
It's definitely the hardware, but of course the hardware, we all predict that will rapidly improve.
Yes, check. So by 2035, you mentioned hardware must be much better than it is today.
Absolutely, yeah. So that's when it gets interesting, right? If hardware is good enough to crack encryption, that's when I also think like, oh wow, if it's that good, I have no proof whatsoever, but intuitively, you might feel like, oh wow, then it should also be good at other tasks. So that's a good motivation to at least look at these optimization and machine learning applications. But you also mentioned software, and yes, I also think there should definitely be more progress in software. I honestly hope that we'll get a couple of algorithmic breakthroughs, that we find new algorithms that are really a significant improvement in how we solve optimization problems today.
Can we dive a little bit more deeper into that?
Absolutely, yes.
So how do you develop a new quantum algorithm? So what do you need to do, and what is the action in the field?
So on a very fundamental level, the way people approach algorithmic research is, well, it's a lot of trial and error, but of course we do slightly better than that. People try to really understand the problem in multiple ways, in a very fundamental way. And to just show you an example in how you can also understand a problem is, for example, to prove that you cannot solve a problem in a certain amount of time, or prove that there cannot exist a certain algorithm that does something in a certain way. We call these lower bounds, and they will show you that, for example, there is no hope in doing better than, let's say, a certain amount of time, or in jargon, a certain time complexity class. And of course, there's also different techniques, right? We have a lot of mathematical techniques. For example, we could map one problem and show that if you can solve that problem, you can also solve a second completely different problem. So these are examples of techniques that we simply try, we experiment with, and we hope that results eventually in an algorithm that solves a problem faster than how we could solve it before.
And what are the biggest bottlenecks at the moment for new quantum algorithms?
Well, there was a couple of years, there was an interesting situation because there was a paper out on arXiv, the repository that all the academics would read, and it would claim that quantum computers could break a certain type of cryptography that we didn't know it could break before. So that's a really big breakthrough. Like end-to-end algorithms there's not that many end-to-end algorithms that really work. So when a new one comes out, that is really big news. It was very rigorous. It was well written by an established, well-respected scientist. And of course, he also wasn't completely sure. So people started looking at it like, is there a flaw? Could it be real? And one of the first comments on this paper was, we're going to check whether it works, but we don't expect this paper to be correct because it does not use any new techniques. It's been using techniques that we have already known for a long time. We've applied them in existing algorithms. We also understand the limitations of these techniques. And indeed, in the end, a mistake was found in the paper, and this specific type of cryptography is still safe against quantum computers. But the lesson I took from that is that if we want to find new algorithms, of course, we're going to look for the algorithms, but we also need improvements in the mathematical techniques that we have today. There's many experts that will say that without these new mathematical techniques, it's unlikely that we can even build the new algorithms.
Yes, and what are the developments in mathematical techniques?
I'm not super up to date about that. You should definitely invite a good mathematician to do this, but I hope I can relay a bit of the highlights that have been there over the past couple of years. So there's a couple of established algorithms. Most of them were invented in the 90s, like Shor's algorithm, Grover's algorithm. I think in the zeros, maybe early tens, we had the algorithm that would help you solve a system of linear equations. I think that's a great algorithmic breakthrough. It shows some new mathematical techniques, but it did not work end to end where you could really input classical data and get classical data out, and then still the quantum algorithm would be faster than, let's say, a GPU. So it has interesting techniques, but it doesn't work as a standalone algorithm. And the past couple of years, people have really looked at what I think is a very interesting technique, sort of an interwoven set of new mathematical techniques. And I think it's mostly well known under the name of the quantum singular value transformation.
So what does it stand for?
Some people have explained it as the grand unification of quantum algorithms. It's not really a new algorithm, but it's a new language to describe the quantum algorithms that we know today. And most of today's quantum algorithms actually fit under this framework. And we can also use it to, for example, interpolate quantum algorithms or generate new quantum algorithms or new variations of algorithms. So we really found a new language with which we can describe the quantum algorithms that we already knew. And that's, I think, a beautiful new example of a technique where we help ourselves understand what quantum computers can do and what they cannot do. I think
do you have maybe 3 bottom-up examples of one bottom-up example, how that practically helps the industry further?
No, I'm very much afraid that this has not much helped the industry yet. It has helped academics. And I think there's a couple of people in industry that really honestly care about the fundamentals of algorithms. But we are still lacking in our task of making this useful. I think a lot of work still has to happen there.
As an investor, I'm not always the one who has the best technological knowledge. I don't have a PhD in quantum technology. But what I do look is at the value chain and the ecosystem. And what I find, Steve Ballmer at some point, he said it's all about developers. And you can track the amount of developers that's following or estimate roughly an ecosystem. And so what you see now is a lot of people are interested in developing applications for GPUs and especially CUDA. So really the momentum of people programming and developing for CUDA is really accelerating. So that's really taking off. If you think in that perspective, can you describe a little bit the basics of the ecosystem on software and algorithms within quantum? Is there a good analogy, or what are the leading horses?
Yeah, I think there's 2 things I can describe. First is a bit about the stack, like what different technology is out there to create quantum software. And then I can mention a couple of examples of big players there. I think it's important to distinguish between what an algorithm is and what software is. And this is kind of technical and hard to explain, but when I look at an algorithm, I really see that as a mathematical concept. It's like a recipe in a book full of recipes, and this book only has text in it. It doesn't actually do the cooking itself. And in the same way, we have quantum algorithm developers that write this down in a mathematical paper, often without any software. And the software is the implementation of this. So I think a good software developer is like a good cook that can look at a recipe, it reads the recipe book, and it actually does the cooking. Or maybe even better, it builds a factory that implements this recipe. For example, if it's a recipe to make a chocolate cookie, it would require a reservoir with dough and maybe some chocolate chips. It would have a big oven. And designing that is an art by itself. So writing the recipe is one side, that's the algorithmic research. And then building the factory that actually produces the cookies, that is what a software developer does in my eyes. And we need both of them. And of course, they need to understand each other.
Clear?
And then, of course, on top of this, I guess most software also comes in multiple layers. So I would imagine that most quantum algorithms are really hard to implement. It requires a lot of skill. You need some knowledge of quantum computing. But I hope that people will implement this in such a way that in the end, anybody can use it. Or at least a skilled software developer can use it, can import it as a library without having to have any knowledge about quantum itself. So I would hope, for example, that an academic that likes to study certain medicine can simply use the techniques that we developed without necessarily knowing all the ins and outs of a quantum computer.
Yes, and IQM, a few weeks ago, they had the state of quantum. What I liked about the report, it was really neutrally written. It was not like a promo of of IQM. I thought it was a fair assessment of the state of quantum technology. And they mentioned that there's a lack of talent of software programmers that understand quantum. And at the moment, there are no good compilers and software libraries that make it really easy for software programmers to write applications for quantum or to write a quantum algorithm. And they see that as one of the biggest bottlenecks for further technology adoption.
I can absolutely imagine. It's incredibly hard to to do proper programming for a quantum computer today.
Can you maybe break it down in first principles? So why is it so hard? Can you explain it in simple terms? So maybe what software libraries are there today for quantum, and what are compilers, and what do they try to achieve? But maybe step by step.
Absolutely. Yes, well, I think most people that want to learn about quantum programming today, they would look at something like Qiskit, which is a language by IBM, or Cirq, with a Q, by Google. And what these fundamentally do is let you build sequences of gates. And a gate is really the most elementary instruction on a qubit. And you should compare that to an AND gate or an OR gate that we do in a classical computer chip. But if you ask any programmer to design an algorithm in terms of AND and OR gates, they'll just laugh at you. That's ridiculous. We don't do that today. Right? What a programmer wants to see is, well, I guess ideally you would have a high-level language like Python or C, and that's relatively intuitive. You can simply tell the software, like, hey, I want to have a number, and it could be a floating point number with some number of digits behind the comma. There could be rounding errors or so, but you would ideally hope that the software takes care of this. You want to have more abstract objects, maybe a graph or maybe a picture or something. But we're still very far away from that. So even if you ask a programmer to go low level, they will point at assembly, which is a language where you really talk about the registers in your computer. You would have elementary instructions like, hey, fetch register number 6 and register number 12, put them together in the CPU, see them as numbers, and I want you to add them together and then store them in register number 13 or so. And even that is way too high level for what we do with most quantum programming today. In fact, for classical computers, we easily figured out like, okay, numbers are probably the most fundamental thing that we want to store. For a quantum computer, I'm not even sure about that. It could also be something with, let's say, electronic states in a molecule or so. Now, there are a couple of more high-level programming languages. I think PennyLane is very often used for machine learning tasks. There is a Classic, which has a package that I think does a very good job in abstracting away much of the low-level programming and making it seem as if you program a high-level language. And then you asked about compiling. I think what most of these programming...
Can you maybe first explain to the audience what does compiling mean?
Well,
Because
maybe I'm a bit... Maybe I'm a bit
confused
confused about this myself, because I always had a simple picture about compiling, but what mostly happens in quantum software is actually transpiling. They prefer to have a different term, so maybe I'm not the expert that should explain this, but I'll try and give it a shot, and please correct me if I happen to be wrong. If I understand correctly, compiling is the act of having like a high-level language like Python. It's intuitive. You just say like we have a couple of numbers and we might add them, and the compiler essentially maps it to some sort of assembly. It says, well, we happen to have this CPU, and the CPU can do certain instructions, but there's also certain things that it cannot do. For example, if I type in Python, let's add 2 numbers, then the compiler will look at that and say, hey, I found an instruction. The CPU can actually add 2 numbers. So let me add this for this specific CPU. I'm going to make a list of instructions for the CPU, and it's going to add 2 numbers. But it might not have an instruction for, let's say, division. So a compiler might say like, division in Python, I've seen that before, but I need to have a whole elaborate list for this specific CPU to do all these steps. So that's what I think a compiler does, or what we use it for. What we do with quantum algorithms mostly is asking the question, if we have an algorithm, but not quite CPU instructions, we have AND and OR gates, how should we arrange these AND and OR gates in order to solve a problem? So this is even more low level. And often we already program sort of in a level of gates. But I really mean, we target a couple of qubits, we know what has to happen on these qubits, and we just need to break it down in the type of gates, the tiny instructions that are natively available to the hardware. So I see a lot of similarities, but if I understand correctly, this is the difference. But please correct me if anything is wrong.
I'm not technical enough. I need to learn more about this. So thank you for your explanation. What I found interesting on maybe if we reach, so the first step is 100 logical qubits, then the first applications are possible. At 2000 logical qubits, you might be able to start molecular modeling and maybe also quantum encryption or breaking encryption. If we even move further, then but what I'm trying to assess is, so maybe taking one step back, sorry for this. What is the amount of programmers and developers that are working in the ecosystem at the moment? Do you know some rough numbers on that, and how does it compare with people working on CUDA or on Python? Or
I don't have hard numbers on this. There might be interesting numbers. In McKinsey recently published a report, the Quantum Technology Monitor, I think it's called. That might be a good resource to look this up. But there's one thing that I'm really sure about, is that the quantum ecosystem is tiny compared to modern machine learning. So I'm convinced that the vast majority of people that program on CUDA, on GPUs, is much, much bigger than those that program software for a quantum computer. There's only a handful of companies that are really actively doing this on a large scale. And even they probably don't have vast amounts of programming teams.
and what needs to happen, Koen, for that amount to increase? Or where are you looking for that you say, okay, now I have the conviction that the ecosystem will grow?
Well, I think the simplest answer for me to give is we need to have a market, right? These companies need to make something that is so valuable that people want to buy it, so that there's a lot of money available, so that there's a clear incentive to make this software more mature, to hire more staff to work on this. And it's very understandable that the market today is small because we don't have good hardware yet. We don't have the proven software yet. So this is something that has to, I guess, organically grow somehow.
So to your point, once it's proven that quantum technology works, then more developers will get interested.
Yeah, or at least I guess there'll be more vacancies for these developers. And yes, I hope that then also more developers will get interested.
What fascinates me, but that is more 20 years out, is the NVIDIA CDO, Jensen. What he mentioned is for GPU, he's comparing CPU and GPU, and he said, if you have the lowest cost of compute, then there will be smart developers and researchers who come up with new algorithms. But he's talking about for GPU and for AI. But my point is, once quantum will have the lowest compute cost, and maybe also not only the lowest compute cost, but also per additional unit of compute, the lowest energy uses, marginal energy use, then I think the smart researchers and developers will also create algorithms for quantum. But I think that's 10, 20 years maybe out before the ecosystem gets more involved. But how do you see that?
Yeah, I think I agree with you. There's an interesting situation, I guess, right? We hope that very smart quantum chemists will start using quantum computers. I hope that very smart people in operations research will start using a quantum computer. But what's in it for them? From their perspective right now, these computers are probably not good enough. So it's understandable that they will just start using GPUs or whatever works best for them. But if at some point it turns out that quantum computers are good for them, then of course I hope that many will switch, right? They will just pick whatever technology works best to solve their problems. Whether that's quantum or not, they probably don't care.
The conditions like software, standards, infrastructure, do we need to build today to apply quantum on a larger scale?
I guess there's a whole package, right? We don't need to focus on just one thing. You mentioned like we need to have standards for interoperability. We need to have a strong workforce. We need to have a good supply chain. But I still think what I would focus on primarily is still nailing the fundamentals. We're still lacking there. So really getting money for better hardware and solving the fundamental problems in software so that hopefully in 10 years we have really good algorithms, candidate algorithms for machine learning optimization. I think the most value would be in that. And of course, the rest should not be neglected, but it should just scale along with the fundamental improvements that we try to make.
Would you like policymakers or industrial parties to understand better about quantum technology?
That's a great question. A lot of things. I think the biggest one is probably the misconception that we discussed before, namely that quantum computers would simply be a new type of hardware. It's faster. Everybody will just buy it, replace their classical computer. I think that's a silly intuition that I heard many times, and I'm a bit worried that this will lead to incorrect decisions. So if policymakers need to know something, it should be that quantum computers will not solve everything. They're good at very specific tasks. They are special purpose machines, and we should treat them like that.
How could quantum technology influence geopolitical relationships? And do you think Europe, the US, or China will take the lead?
I'm definitely not an expert on this, but I guess unfortunately we're already seeing a lot of geopolitical influence. So quantum computing is often seen as a dual-use technology. Some people say that because these optimization and AI techniques can be applied to, let's say, drones or other types of warfare. Of course, there's the whole encryption aspect. So if I understand correctly, I think the United States has already published a limitation on the export of quantum computers. They cannot export quantum computers of more than, let's say, 105 qubits, if I remember correctly. Either way, it's a very small number, and it's absolutely obvious that you cannot do anything useful with these computers. But this is also a bit disappointing because we need to have the smartest people together. I think historically we've seen that technological improvements go a lot faster if people around the world are working together. So this is really halting the innovation a little bit. Another kind of unfortunate thing is that if you look at IBM, which has arguably the most mature quantum computers, if you look at their terms of service, there's a vast number of countries that are completely excluded. So if you are in, let's say, India, China, Pakistan, you can most likely not use IBM's quantum services. And this is really a significant fraction of the world that does not have access to their computers. So these geopolitical considerations are already in effect. I'm not sure why IBM does this, whether this is something that they have to comply with due to law or whether they decide this for themselves. I cannot judge. And you were also asking about who will take the lead, right? Is it going to be, we feel that there's intuitively some competition between Europe, America, China. I honestly don't know. Everybody has their pros and cons. For example, America has by far the strongest commercial ecosystem. They have the big players, IBM, Google, Microsoft, Amazon, that have by far, I think, the largest investments and maybe also most patents on quantum computing. China has really impressive government investments. And also in the field of quantum networks, they are probably leading in the sense that they have more knowledge, more academic papers, more world-first achievements. And that makes maybe a bit of a sad picture for Europe, right? We're not leading in any regard. I do think we have a nice position. We're prepared. Yeah, we're kind of on the way to have a substantial ecosystem. We can deliver parts. We make good software. Maybe it's not going to be our milk cow, but some people are extremely pessimistic about Europe. I'm not incredibly pessimistic. I don't think we're leading, but I think we're a player that should be taken seriously.
One of the things from an investor perspective that I focus on is what is the access to capital. And a good example of that is, for example, Elon Musk. He had definitely access to capital.
Absolutely.
With Tesla. Tesla, compared to other car manufacturers for a very long time, was loss making, burning cash, and he needed constantly rights issues to attract new equity. But people believed in him, and that's why he had access to capital, and then that's why he could invest. And with his investment, he leapfrogged the industry, and that's very powerful. But if we then look at the venture capital industry, Europe is only 5% of global venture capital, and venture capital companies don't put all the money in quantum technology. So that's really a problem, I think. And also the big institutions don't like to invest in quantum technology because there's technology risk, there's time horizon risk, and that's something that slows down the development. So on access to capital, I think Europe really lacks. And the other element, what I don't like about Europe, is that the research institutions like TNO in Europe, they're really divided. So in the US, they, for example, one program, I have multiple programs, but one of the programs, for example, with DARPA, they really try to bring everything together. That's really powerful. And that is the risk in Europe, is that we are too spread out and that we miss eventually. What is your view on that, Koen?
Well, I'm by no means an expert on investments or venture capital, but I definitely recognize that the startups that I speak to in the Netherlands and in Europe, they are kind of jealous about the US, where it's much easier to get a much bigger amount of money for literally the same idea, for literally the same company. So that's sort of an unfair advantage that the United States has. Whether we are more divided, I'm not so familiar with the American ecosystem that I can really judge. Do you see that do you see any ways that we can learn from them to be more,
Now,
work more together?
For example, if we look at the telco industry, every country has its own regulator, but also its own R&D roadmap. And it's much more efficient if you have one regulator and one technology research house. And maybe it's good to have two, but in Europe, but if every country has its own, and then they want to protect its own jobs because you have one boss and you have one, so then it's you optimize for the optimization is different. And if you put all the local research budgets together, you would have a much bigger budget, and if you then make bold decisions, you might be able to have more impact.
So maybe the European Union could also start some sort of an ARPA challenge-based program where they really follow one vision and fund precisely what would contribute to that vision.
I'm not the expert how to do that, but I think more coordination in that could really bring forward the technology. And I think also in the Netherlands, now I think the quantum delta participations, that was also part of the success why we have a good ecosystem now here. I think, yes, there were excellent technologies, but there was also because of government funding that we have now 26 startups in the Netherlands on quantum technology. Without that support, I think it would be really hard. And now those startups are scaling up.
Yeah, they really filled a funding gap that we lacked in the Netherlands and in Europe. Absolutely.
That's because it's early stage and there's technology risk involved. but I'm proud on what has been achieved so far in the Netherlands as a Dutch citizen. But okay, maybe we're talking our own book.
Yeah, we're a bit biased, of course, but I do think
Yes.
the Netherlands is a good example that, we are always looking up at the bigger countries, the US. I think France has incredibly interesting startups like Candela, Alice and Bob, Pascal that have the potential to become world leading. We are a bit tinier, but yeah, I think in specialized knowledge, components, maybe also in software, yeah, we have really high potential.
Where does the Netherlands stand worldwide when it comes to quantum algorithms or quantum software? And where can we distinguish ourselves?
Yeah, it's a bit harder to measure how important you are with regards to science or even with algorithms, right? Because algorithms, it's kind of hard to make money based on that. We have had a couple of really successful software startups. For example, Q&Co was an incredibly interesting company. They got bought by Pascal. So I guess now their software team is incorporated in the bigger Pascal organization. Fermionic is doing great work worldwide. There's a couple of much bigger quantum software startups like Multiverse Computing. QCware, I think, has been doing fantastic work. Both of these, by the way, are European. No, I think QCware is American, but they also have an office in Paris. Multiverse, I think, is Spanish.
I don't know. I need to check.
But yeah, overall, the software ecosystem is a lot smaller today, understandably, because who wants to buy software if we don't have the hardware yet? So that's maybe a very interesting area because as the hardware becomes available, what we've also seen for classical computers is that previously hardware was sort of the challenging thing to make. Building the computer was challenging. And then once you had the money together to buy a computer, you would just have people do all the tedious work of programming the computer. But today, if my laptop breaks, I would just buy a new one tomorrow. And I can be guaranteed that it's identical, that it will just work, and it's become a commodity. It's relatively cheap. But if my IT system breaks, that's a disaster. That requires a lot of manual labor from programmers, from IT staff. So I think today the market for software is a lot bigger than the market for hardware. And I guess that's also a shift that we're going to see in the future. And whether Europe or the Netherlands is well positioned to conquer that market, I find that really hard to say. I don't know what indicators to look at or how to compare the kind of knowledge that's available at different locations.
And Koen, innovations and breakthroughs are typically very related to people. It's quite people business. Which are the key people that you track? Who are the leaders that you follow? You say, well, if they speak, I need to pay attention.
Well, most of my news I just get from common news outlets like Quantum Computing Report or the Daily Qubit or so newsletters. But if I have to mention specific people that I follow, I think in the field of algorithms, Scott Aronson is a professor in the US that is really authoritative. He has a very interesting blog. I think you can find it on, I guess, scottaronson.com. Or if you search for it, it's easy to find. And he has
Multiple people recommended to follow him.
Yeah. And another person that nearly everybody follows is John Preskill, also an American professor. And he, for example, coined the term NISQ, Noisy Intermediate Scale Quantum. He is also, I guess, seen as a visionary when it comes to the next steps. Like, how are we going to slowly get to early quantum error-corrected devices? I think these are probably the main sources. And what, as a special mention, I really like the website Stack Overflow and the different sub-websites that they have. And if you have a specific question about quantum computing, it's often on there and they have fantastic answers, typically from researchers, academics, or from people that work at quantum companies. And for example, Peter Shor is or has been relatively active on this website. There's questions about Shor's algorithm or even how it came about. For example, how did Shor discover his algorithm? And Peter Shor himself is answering that question. So that's also a fantastic source of information.
Thank you for sharing. Koen, you mentioned you had multiple hats on, among which quantum key distribution, but also you're writing a book, but also that you say you're trying to coordinate to make Amsterdam a quantum hub. I think last week or 2 weeks ago, you organized a startup conference or students who could pitch to become a startup. Could you explain a little bit that and what did you learn from that? Did great ideas pop up?
Yes, we have at the University of Amsterdam, we have a brand new master program that's called Quantum Computer Science. And here I really want to underline the computer science. We're really looking at the mathematics, the algorithms for quantum computers. And this is a brilliant program because if you want to understand how a quantum algorithm works or how you can really do proper error correction, you really get to see the ins and outs. As a downside, we don't focus too much on hardware. You don't get experimental skills. So we really target people that are extremely good and interested at mathematics, logic, computer science. And as part of that program, we have, of course, many technical subjects, but also a course called Quantum in Business. And this is a soft skill course. So the goal is that students learn some intuition, some knowledge about how the non-academic world works, how to work in a company, how companies, for example, try to sell quantum computing, what the value proposition is of different technologies. And as an assignment, they actually have to conceive their own startup, think like a startup, try to come up with a fantastic product, a fantastic business model, and they pitch this to an imaginary investor during the final presentation session. So this is I think the session that you referred to, which is very interesting because we often have external guests that are interested. We often see very, very interesting creative applications. For the purpose of this course, it's kind of okay if it's slightly unrealistic, as long as they nail the things that an investor wants to hear. But I heard some very interesting proposals. For example, quantum dots are very versatile devices. Maybe we can use them to generate very specific UV light, which is currently very technical to make. Or maybe we can make sensors to investigate the soil of farmland and to measure how many nutrients are in there, how moist it is, whether there are any pollutants in there. And this could make farming, for example, more efficient. We might use less fertilizer if we don't need it. Or we might be able to feed the plants right at the right moment with the right nutrients. So these are, I think, very creative ideas that are definitely worth looking at a lot more.
And what is the follow-up on that? So those students have great ideas. How can they get funding?
Well, I have to be very honest. So far, nobody actually started with a startup out of this. And if I'm totally honest, I would also recommend the students to first maybe do a PhD or to further specialize in this field before they actually start this company. But it's definitely possible that already at, let's say, a bachelor or master student age, people could start a startup. What I always do recommend them is to team up with somebody that has very deep technical knowledge. Maybe a professor, maybe somebody who just graduated from a PhD. And the first steps of funding are typically kind of small funds just to make sort of a proof of concept. And for example, I think most European universities will have an internal fund for that. So this is probably pre-seed funding. And I think this is not typically something that the big investment companies will be looking for.
Okay. Koen, maybe for investors, why should investors follow you? And what can you bring to the table for investors?
I don't think people should follow a specific person or so. I think you should follow a good source of information. So I would definitely, of course, I'm biased, but I would recommend reading at least the first chapters of introtoquantum.org, which I think is the best possible introduction to quantum computing that I can give. And I made a whole list of resources on that same website, depending on what your taste is, whether you want to learn the technical details or learn to program or follow what businesses are doing. And I'm trying to keep that up to date. So it's not just a book that's published today and next year it's outdated. No, it's constantly updated. So I think that's definitely a list of recommended sources that at least I recommend and I frequently use myself.